My name is Jennifer Santana. I'm really excited to be here with you guys. So a little bit about me. Who am I? I am a cytogeneticist at City of Hope. We look through microscopes a lot. I'm the lead technologist there. I've been there for 14 years. So I came in as entry level and worked hard, worked my way up, and now am proud to be lead technologist, which means I oversee a lot of the stuff that goes on in the laboratory. People come to me with questions. It's really very rewarding. We have a lot of fun at City of Hope. This is a picture that we took for our lab week. We celebrate Laboratory Professionals Week every year, and it's a week long of events. This was a photo contest, so all these people right in there, these are all my coworkers and all my laboratory coworkers. That thing in the middle is actually a chromosome. So do you guys know about genetics yet, or still learning? Still learning, okay, no problem. So we painted that. That's actually a chromosome. That is the banding pattern of chromosome number 1, because we are team number 1. We didn't win the photo contest that year, but we had a lot of fun doing it. So this is a little bit, I'm going to explain a little bit about what I do. Here's a little video to show you the chromosomes.
Genes, DNA, and chromosomes are what make you who you are. They are the set of instructions that are given to you by your father and mother. These instructions are in your cells, and all living organisms are composed of cells. There are many different types, like nerve cells and hair cells and skin cells. They all have different shapes and forms, but every cell has the same basic parts. The cell has an outer border called the membrane, which contains a liquid material called cytoplasm. In the cytoplasm is the nucleus, and inside the nucleus are chromosomes. In humans, each cell normally contains 23 pairs of chromosomes.
All right, that's all I wanted to show you guys. So this is 23 pairs of chromosomes. This is a normal, well, you can't actually tell, but this is a male person because we have the X, and that little thing at the bottom is a Y. Females are XX. So this is in every single one of your cells. So this is a metaphase, and this is what we look at in my department in cytogenetics. You can see over there you have the metaphase right there on the left, and then on the right, that's how we pair everything, and we match it according to the computerized version to see if everything matches. So all of these chromosomes look the same in everybody pretty much. So this is a normal male, and the normal females have the same, we call them banding patterns. So I'm also your Water District Board member. I was just elected in 2018. This right here is a picture of Morris Dam. That is water that is running down. That was captured, local rainwater. And there's a little outlet that you can't see right here. And that outlet is spewing water. If you guys go down the 605 and you see the water on both sides, that's the water coming down. Local rainwater and the water from USG3 is what we call that. And that is from up north, all the way up north. So we import about 20% of all of the water we use into our basin. One cool thing about this is there's a lot of engineering jobs in this one, in the water district. Me growing up. I grew up in 2 places. I grew up in New England, and then I also grew up in Southern California. New England, I grew up in a very small town. Lots of farms. I had to drive 20 minutes to high school. 3 towns went to the same high school. So it was a really small community. And then, of course, Southern California, there's a lot more going on. You know, not too many farms in this area. And no snow. If any of you have been in snow for winter in New England, it's pretty harsh. It's fun to go up and be in the mountains every now and then. But if you're there for, 3 months, it gets pretty bad. So this is kind of what it looks like, New England. Lots of water, lots of rain. So my dad was the first in his family to go to college. Everyone else went into, they got engineering jobs, etc. Electrician jobs. So he was the first to go to college. And he didn't have a lot of support, but he wanted to, so he did. He went to college, he left his job. And he ended up finding a passion in chemistry. So one of his first jobs out of college was disposal of waste, chemical waste. So they gave him this silver nitrate. The company he worked for gave him a ton of silver nitrate to dispose of. Being the chemist that he was, he actually took it and, with his knowledge of chemistry, converted all of that chemical waste into solid silver. And with that solid silver, we made money to buy our first house. So he was a very resourceful guy. He saw outside the box, and it was pretty inspiring. So this is my brother. He grew up in this chemistry background. He used to do experiments with my dad, including that one. And he ended up growing up and going into chemistry, finding a passion for chemistry. And of course, his daughter, my niece, might follow in her father's footsteps. And actually, this is a picture of him in his laboratory. So he's a doctor in his laboratory. For me, I wasn't always interested in science. I had other interests in high school. I really liked painting, writing, arts and stuff. I like to play with music. So there was a time where I was considering just going into art, going into music. This is the painting I did. That's me in high school. This is a painting that I did that won an award. I was able to get it hung in a museum in Boston. So I had these other options I could have gone into, and I'm sure you guys do too. But in the end, I really didn't want to, I didn't want to make my passion, or I didn't want to make this hobby of mine, and I didn't want to make a career out of it necessarily. I didn't want to do it 40 hours a week. And so, I gave other subjects another chance. So I went to the science fair. This is my 10th grade project. I didn't know what to do. So I asked my dad, "Dad, what do I do for a science fair project?" And he said, "Well, there's this neat study where if you cross your hands, then you're going to find a comfort zone. Either your hands are intertwined right over left or left over right. And one of them feels really awkward. And one of them feels normal because it's genetic. It's Mendelian genetics, I believe. So if you're left-handed and you cross your hands like this, and you're 25%. If you're right-handed and you cross your hands like this, and you're 75%. So we knew this. This was actually a published thing. My dad said, "Oh, go ahead and just do it." So I interviewed a bunch of students. I spent a lot of time, classmates. I spent a lot of time doing this project and putting this together. And I wasn't really passionate about it. We already knew the outcome. I was going through the motions, putting it together. And that came across when I was being evaluated for the science fair. They said, "Oh, wasn't that already discovered?" I said, "Yeah." So I got an okay grade. I think I got a B. For my next science fair project, I decided to do something that I was interested in. And as an artist, I was interested in colors and etc. So I was interested in how color affects learning. I came up with my own project. I picked up a construction paper at Michael's, or whatever Michael's is over on the East Coast. And I made these flashcards. I had warm flashcards, which were red, pink, yellow, and I had cool flashcards, which were blue, green, and yellow, because we only had those colors in the pack. So I had these colors, and I wrote different words on them, and I interviewed all my classmates. I said, "Okay, what do you think of when you see this? What do you think of when you see this on the different colors?" And that was part of the test. The other part of the test was seeing how fast people go. If you put it on how fast they can do a math problem if you put it on a cool color versus a warm color. I had a ton of fun on this project. I got to interview my classmates in something fun. I learned a lot about them. And sure enough, I won the science fair that year for the entire school. So that's, all 4 grades. The point is, you can apply what you are passionate about, what you love about in science, and using the scientific method, you can find things out that are really interesting. And once that interest really translates to the people that are actually judging you. This is a screenshot of something that I found online. This is a project that I did back in 1998. So it's pretty neat to look that it's still something that's interesting, and people are interested in today. Growing up in Southern California and the East Coast, I had always wanted to go back to California because I think it's awesome here. I love the San Gabriel Valley. I love all the people. I love Los Angeles. So my motivation for getting good grades in school wasn't always about trying to get that A. For me, my motivation was getting good grades so that I could get into the school that I wanted to in California. So when things got kind of tough and I didn't feel like studying, I wanted to, just relax, I kept that in the back of my mind. Well, I have to get good grades because I want to get out of here. So I studied. I wanted to go to a public school, and for out-of-state students, it's much more difficult to get into a public school. So sure enough, I was able to go to UC Davis, and I'm really happy that I did. It's a great place up north. Has anyone visited UC Davis? There's a ton of really interesting things up there, really interesting people up there. And a lot of people from LA actually go up there too. So the best part about any college is you're not just taking classes on your major. You are being exposed to things that all different fields, all different genres. I took a political science course, I took a history course, I took some music classes up there, and some hard sciences, some chemistry, stuff like that, sociology. So you're being exposed to all these different fields so that you can kind of find out what you're interested in. And for me, it was when I took biology, actually. It was my third quarter at UC Davis as a freshman. And I took this class, and I was just blown away at how you can look at an organism and break it down the way they broke it down, and what you can learn about living things when you break it down into a science way. So that was really a big moment for me. I studied really hard for that class. I did not do very good. I got my worst grade that I'd had since I had gone into college. But I was passionate about this. I was intrigued by this. I knew this was something that I could dedicate my life to. So 3 years later, I graduated from UC Davis, and I got a degree in biochemistry and molecular biology. And this is what I do now. We came down to Southern California. I had a boyfriend in college. He proposed. I accepted. He's from the SGV, so we moved down here. I've been here for 14 years. And in June, I graduated from college in 2005. By July, I was working in Cytogenetics. This is a presentation that I give now to people that come into our laboratory. So I'm given this a few times. I hope you guys enjoy it. So this is what I do. That's my title, CCGS. That's a license that I got in the Cytogenetics department. What we do is we look at these metaphases. On the left, you can see the metaphase. On the right, that's another branch of pathology that you can go into. Medical technologists do this part. They help with the pathologists to prepare these slides. What you're looking for here, this is a metaphase, and that's that banding pattern I had showed you guys. This is a patient that has acute myeloid leukemia. And we know that because of that little tiny band right here. This is actually an abnormality. It takes a long time to recognize this stuff. And again, this ties back into my love of art, my love of visuals. So when you get skilled at looking at this, you're able to pinpoint that. But it's just a part of the picture of pathology. Because we have that slide I showed you of the morphology slides. This one. A lot of people miss this in my field. But over there, that's actually very easy to catch morphologically. So if you know what the other person's doing in the other lab, then you're able to look for that band. So what we do is we prepare these flasks. We incubate them with blood and bone marrow. Bone marrow is what creates blood in your system. And we put them in an incubator which grows the cells. We put them in there for either a day to 4 days sometimes. Then we'll treat the slides, we'll stain them. This is a little AT-rich areas, or basically everybody looks the same. This is probably, I can't tell you if it's a Y chromosome in there, but it's either a normal female or a normal male. And there is no computer program yet that can do this. This is all by human sight because it's just so complicated and there's so many patterns that you have to memorize. Here we go. This is a normal male cell. I think I showed you this one already. And this is an example of abnormalities. So what we're looking for, patients that have cancer, they have cell mutations. So those chromosomes can be mutated. And in this patient with acute myeloid leukemia, we have an abnormality here that's actually really difficult. So this text right here, this is why it's really good to understand math and know all your math skills. This right here, it's just 45, so you know it's not the normal 46 complement, minus Y, which is the Y chromosome, and then it goes through all of this stuff. This basically is a numerical representation of what that picture is. So if I were to say this karyotype to someone in the field, then they would understand that I'm talking about this. So the subtlety here is right here on this guy, looks pretty short, and it's translocated up at that number 1, which you can't really see. A lot of people would miss this, but we have other techniques to figure that out. So they can be pretty subtle, or they can be really complex. So that one over there is a sarcoma. And all those things at the bottom, there's so much going on with that cell. It's so different from the 46XX, 46XY, that we don't even know where to place this stuff. So we put them down at the bottom. And again, no computer program can even do as good as that. This is our little handbook that we have. So we match the banding patterns according to that. So you can see this is a chromosome 2. And you have this matching to that, etc. So it takes a long time to really understand this stuff. So this is a really interesting case that we had come through the lab. This patient has multiple myeloma, which is a bone cancer. They have a lot of different things going on, as you can see. This was something that we knew they had. This was pretty much what they had had previously, but when I turned the case in, and I did this case, when I turned the case in, somebody said, because we have a lot of people looking at it, what's going on with that? Right there. It's really small. I thought, oh, it looks kind of normal to me. Maybe it's just broken a little bit. But sure enough, we did what's called fluorescent in situ hybridization. So this puts little fluorescents, green and red, onto the chromosomes. And we were able to tell by this, there's that called a fusion up there with the red and the green together. That's normal. The separate red from the separate green, that's abnormal. So by this, we're able to look at this and realize that that bottom part of the chromosome 8 went to the chromosome 3, which then went to the chromosome 21. So it's called a 3-way translocation. Bottom of the 8 went to the top of the 3, top of the 3 went to the bottom of the 21, bottom of the 21 went to the bottom of the 8. So you're always learning stuff in cytogenetics and, pretty much any science field. References, anybody's interested. So that's the stuff I do. But why go into STEM? Because STEM is a mindset. STEM is a way of looking at the world and seeing things from a different perspective. It takes a long time to learn the language of any branch of STEM, but it's very much worth it. Once you learn it, then you don't see things the same way again. And there's a ton of career options out there. The job market for STEM is humongous. And you can go anywhere from entry level, if you wanted to go for your PhD, you can do that. You can do anything, really. So career options, you can become a coder, computer programmer, video game designer, etc. Aerospace engineering, SpaceX, that's a pretty good company coming up. They had the rocket go up recently. I don't know if you guys saw it, but that was kind of cool. And then here's some engineering stuff. You can find innovative solutions to some problems. Here, this is a biochemist at UCLA and an internship, which is, of course, my favorite, biochemistry. So learning about the cell, she's got a pipette in her hand, all that lab coat, all that stuff she's wearing. It's called personal protective stuff, PPE. I forget what the E stands for. But this is the kind of stuff that you could be doing. And there's a lot of fun jobs that you could be doing, too. that pay pretty decent. Toy designer, food critic, fortune cookie writer. You get paid for this stuff. Somebody's going to get paid for this stuff. So final thoughts. STEM is about understanding how the world works. And it's ultimately a state of mind. It's asking questions, finding better ways to solve problems, and we're going to be facing a ton of problems in our lifetime. One of them is water. You know, we're always going to have a shortage. We're always going to be on a drought. You have a lot of things coming up that we're going to have to take care of. And I'm very happy and excited to apply what I have learned in my career into this field that I just came into in 2018. And so I hope you guys will consider lending some of your talents and your unique perspectives into this field that's going to be ever expanding in STEM. So that's it. Thank you.
That was very, very impressive. Does anyone have any questions?
I have a question. What is something, since you work on the water board, what is something that you would like everybody to do or know about water?
One of the big things that I want people to know is that the water here is actually very clean, and you can drink it from the tap. It's one of the cleanest basins in the world. It was not always. They created what's called the Water Quality Authority back in the 90s when they found some contaminants in there, and they did a great job cleaning this up. So now you turn on your tap, you can drink that water. And that's a good thing to keep in mind when you have bottles of water. You know, we can reduce our waste by just drinking from the tap, by refilling your water bottles, etc.
We actually have hydration systems here on campus now.
Oh, good.
Where the kids could just put their water bottle in the hydration and get the water from it.
Water bottle refill station?
Yes.
Awesome. Yeah. We're going to be putting one of those in on the SGV trail, on the bike trail right there, hopefully. Yeah.
So if you guys can drink that water, that's probably better for you.
Mm-hmm. And I would like to say that one thing you guys should consider when you're going into STEM, you know, look at what your end goal is going to be. You don't always know what path you're going to take, but I work as a cytogeneticist. I came in as entry level. There's this great career called clinical laboratory scientist. And it's something that you can go into as a trade right away, where you can work in the pathology department after, you know, 2 to 4 years of college. And they offer that program at Mount SAC. So there's a lot of options, and it's great pay and provides a good life.
And it's about making a difference, because you're working with cancer and you're looking for that,
Oh, yeah.
that discovery that will help people, that will help cure cancer. You know? So it's pretty cool.
How important do you think math is for you?
It's huge, yeah. If you got to know the basics. If you didn't know, you can tell the people that have the basic understanding and that had put the time in, and those that did not in my career. I can see, and it's simple things even. It's like, this should be a 48 xy plus 8 plus 10. So it's really huge. It's really huge. As far as conventional cytogenetics, which is what I showed you with that metaphase, the problem is, if we wanted to detail everything, then it's a lot of money we'd have to throw at it. So as far as what you need, we have this thing called microarray now. It's a new technology in my laboratory, and you're looking at pairs, base pairs that are at a much smaller scale, so you're able to pick that stuff up, but you have to have X amount of what's called tumor burden. You have to have X amount of cancer cells in your system. For the metaphase, I'm not really sure if that's ever going to be possible, because there's so much variation in it. There's so much variation in the patterns. You have to say, okay, that looks like a band, but it's an artifact. Let me look at these other cells. Sure enough, it's an artifact. Artifact is something that's on the slide that makes it look like a band, but it isn't. And you're not learning, I mean, the way that the chromosomes split is completely different. I don't really know that we'll ever fully be there. I mean, we have a computer program that supposedly you click the button and it karyotypes everything, but even in a normal cell, it's 50% wrong. Yeah.
Thank you very much.
Oh, thank you guys. Appreciate it.